there. Yep. Okay, so like I told you, what I want to do is I'm going to be giving you guys a little bonus video here of a couple of those little odds and end things I told you that I wanted to make sure you guys have. So, you know, when you get the link for this, I guess you already have the link because you're here now. You can just look at these things. And this is going to cover a couple things that I want to make sure you know that we didn't get to in class. Okay, so let me now go to the present now. Do the entire screen. Do the screen share. Now it should come up in a second. We're doing the screen. Okay. So, where are we seeing that other window? There we go. Okay. All right. So, first thing I want to go over with you is, if you remember, if you recall from chapter 5, chapter 3, section 5, there was this problem, number 17 on page 257. And this was the problem. And I think, you know, we went over this in class, online class, so we can make it into one natural log. Then we could combine it into rewriting it, the base is e. So we could rewrite it if the log of this, natural log of this equals 2. That means e to the second equals this, right? And like in any equation, the idea is we want to find out what x equals. But remember, we also have e involved, and e is a number, but we just want to leave e in the answer, because we don't want to, you know, just estimate e. We just want to keep it as e. So the question is, how do we get x all by itself in terms of e, right? And I think the book went right from this starred line down to the answer. So this is going to, and again, I think I already sent you this, but I just wanted to go over this with you briefly. So the way you want to solve something like this, the way you want to get x by itself is like this. The first thing you do is, and this is a general rule in general when you're working with these kind of equations where it's a numerator and a denominator, get rid of the denominator. So we're going to multiply both sides by x minus 1. So that'll give us x minus 1 times e squared, and that's going to equal x plus 5, right? Then we use the distributive property. Now, the reason we're doing that is because we want to get the e squareds kind of, see, this e squared is linked to multiplication with the x minus 1 here. We want to get them as separate parts. So we're going to get e squared times x minus e squared times 1 equals this, right? Okay. So now what we do, the next thing we do is you bring all, because remember, we ultimately think of it this way. We want to solve for x, right? So we got this now, right? So what we want to do now is bring all the x terms to one side and bring all the numbers to the other side. Now remember, e squared is a number, right? It's about 2.7 squared, right? So if we bring the x to this side, subtract from both sides, and at the same time, I'll add e squared to both sides. So now we have all the x's over here and all the numbers, plain numbers over here, right? Okay. Now, this is one of the key steps. To get x by itself here, notice we can factor an x out of this, right? So if we factor an x out of this, this is going to be x times, in parentheses, e squared minus 1. Now, we just divide both sides by e squared minus 1, and this is the e squared plus 5, and there's the answer. So x, in terms of e, will equal e squared plus 5 over e squared minus 1. Okay? So I just wanted to show you that, because I know a lot of you probably maybe never saw that in algebra, how to get x by itself here in a problem like this, and then particularly if there's an e squared here, which is really just a number, but if that number is just kind of coming along for the ride. So that's the key here, okay? All right, so I wanted to go over that with you. All right. Next thing I want to do is look at a couple of those homework problems we didn't look at. But one of the ideas I just want to go over with you, I don't think we mentioned yet, is this idea. And this, what I'm going to say here for sine would apply to cosine or tangent, which is if you say you want to take the sine of an angle, and then you want to do the sine of the angle times the sine of the angle, right? So in a sense, you'd be saying the sine of the angle, that whole thing in parentheses, squared, right? So this would mean sine of theta times sine of theta, right? That's clear that that's what this means, right? Because it's in parentheses, the whole thing squared. But a lot of times what we'll do in trig, if we want to write this, we write it this way. In other words, sine of theta with a little squared sign right between the sine and the theta. No parentheses, right? It's just a special way of writing it for trig. So just you understand, this means, when you see this, this means this. So sometimes I might write it this way just to kind of emphasize it to you that that's what it means. But a lot of times you'll just see it written this way. But it means sine of theta times sine of theta, or sine of theta squared. Now, if you see this, right, just sine of theta squared, what that means is sine of theta squared. So it's whatever theta is, whatever that number is, there's an angle, you'd square it, and then you take the sine of that angle, you see? So just make sure you don't get these ideas mixed up. So in general, if you want to, and the same thing on your calculator, because if you put in your calculator, if you want to do sine of theta squared, do it this way. If you want to do sine of theta times sine of theta, do it this way. If you really want to do just sine of the angle squared, do it this way, okay? And a lot of times when you want to write this, we write it this way, right? Just sine, a little squared sign up there. That means sine of theta times sine of theta, okay? All right. I would say any questions, but I guess there's no one here, so there wouldn't be anybody to answer the questions right now. But again, if you have any questions on this after you look at it, feel free to send me an email. All right, so I wanted to go over these two homework problems we didn't look at yet. So again, right away, don't forget, we know already, remember, don't forget that in the unit circle, we already established, because you could always make that right triangle, that x squared plus y squared equals the hypotenuse 1 squared. But x is the cosine of the angle, so I could say for any angle in the unit circle, cosine, remember this means cosine theta times cosine theta plus sine squared, sine theta times sine squared. You know, this is sine of theta times sine theta. But remember, sine of theta is y, so it's like saying, you know, the y squared, the triangle, they're always going to equal 1, right? And remember, that's just the Pythagorean theorem in disguise, right, for any angle. So in this problem, they say we have an angle, and the angle is in the first quadrant, because remember, pi over 2 is 90 degrees. And they say the cosine of the angle is 2/5. What is the sine of the angle, right? Okay, so we know that for any angle, cosine squared is 2/5. That's cosine of the angle, plus the sine of the angle squared, which we don't know, right, because we want to find the sine, that equals 1. So what this really becomes now is just a little equation that we're going to solve for the sine of the angle, right? So basically, this is just going to be algebra here now, right? So we're going to do sine squared here, right? Just subtracting 2/5 from both sides is equal 1 minus 4/25 when we square it. So that means sine squared equals When you subtract here, this is going to be 21/25, right? And that means that if this is sine of theta squared, sine will equal plus or minus. Don't forget, when you have a problem and it's something squared equals a number, the number could be the positive or the negative, right? So sine of theta equals plus or minus the square root of 21/25. But now remember from algebra, square root of a over b is the square root of a over the square root of b, right? Square root of 25 is 5. So the sine of theta equals plus or minus radical 21 over 5. But since we know that we're in the first quadrant, right? They told you that. That means that if you're in the first quadrant, the sign is positive. So we're going to reject the negative possibility. I mean, it could be down here, but we told us we're in the first quadrant. So it would look like this, right? The 2/5, that's the, for the cosine, that's the x value. But the y value is going to be the sine, and that's going to be positive radical 21 over 5. Okay, so that's how you do a problem like that. Okay, then the next problem I wanted to look at was this one, number 32. And in this problem, you're given this angle. I think, let me just look at what it says again. I'm sorry, 30, yeah, I think 32, right? So it says, let this be an acute angle between the positive horizontal axis and the line with the slope 4, right? Okay, so it's saying evaluate the sine and cosine of the angle. So, here's the positive x-axis, and here's a line with a slope of 4, right? Now, remember what I told you. The slope is another way of thinking about the tangent, right? Because slope is rise over run, right? But again, if you're looking at the right triangle here, the rise is the y, the run is the x, right? So now this is the key step here. Here's some angle, right? And let's make it in the unit circle. So make this 1, right? Remember, it doesn't make any difference how long you make the line, because no matter where you measure the coordinates to get the slope never changes on a line, right? So the ratio of the y over the x is always going to equal 4, right? But now this is the key step. We don't know if we have a radius of 1, right, what the x and the y numbers are. But we do know that when you divide them, it equals 4, right? So what that means is the y number has to be 4 times the x number, right? So instead of writing x comma y here, you really couldn't figure out what x and y are. But I'll show you now. If you say that this is x, since the slope is 4, the y number has to be 4 times the x number, right? Like if this is like, I don't care how long this is, doesn't make a difference if it's 1, if it's 20, I don't care how long this is. If the x number was, let's say, 5, the y number would have to be 4 times 5, or 20, for the slope. 20, for this number divided by this number, 20 over 5 equals 4, you see? So it's always x and 4x if the slope is 4. Okay, now since we're looking to get the sine and cosine, let's say we're working in the unit circle here. So that means, again, we know that x squared plus y squared, which is 4x, equals 1, right? Or 1 squared. So now, again, it's just algebra, right? This is going to be x squared. This is 16x squared. 17x squared equals 1. So now it just boils down to algebra. So x squared equals 1/17. That means x equals plus or minus the square root of 1/17. That means x equals square root of 1, which is 1 over the square root of 17. This is just algebra stuff. Multiply top and bottom by radical 17 to rationalize the denominator. So we get square root of 17 over 17, right? So now, again, we know we're in the first quadrant here, right? We're in the first quadrant. So now if x is radical 17 over 17, because remember, we're in the first quadrant, we're going to, again, reject the negative one. That means that, and again, we know we're in the first quadrant because it says in the problem, the angle is the positive x-axis and then this line that has the slope of 4. But remember, like in any algebra problem, once you know what x is, you can then figure out what y is. Just go back to right here because we know that y is 4 times x. So if this is x, y is going to be 4 radical 17 over 17, right? So the sign is going to be the y coordinate, which is 4 radical 17 over 17, and the x coordinate in the unit circle is going to be the cosine. So the cosine of x is what we solve for x, radical 17 over 17. Okay? So I just wanted to go over those problems with you from homework. Okay? All right, now let me just finish going over the notes with you. A couple little things we didn't get to finish. Okay, so here's another little problem. Again, in the right triangle trig. I just want to show you, like, if you knew that this angle is 53, let's say 0.13 degrees, here's your right triangle, and you want to solve for x, right? Now, this is an example where you could actually do this using the Pythagorean theorem. And if you do it using the Pythagorean theorem, you will see that this side exactly comes out to be 15. So I'm just showing you this because there's a little rounding error, how it works out, because you can use the Pythagorean theorem just to check it. But a lot of times you might have a situation where you want to, you're forced to use the trig method because you only know one of the two sides of the triangle, the right triangle. So let's just look at it. Suppose you wanted to use trig here. Now, you could do it one of two ways. You could say the cosine of 53.13 equals the adjacent over the hypotenuse equals 9 over x. Or you could say that the sine of 53.13, which is the opposite over the hypotenuse, is 12 over x. So if you wanted to do it using trig, you can really use either way, you'll get the same answer. See? So I think I'm doing it using the one where I'm using the sine. So again, I looked this up on the calculator. Make sure your calculator is set for degrees. I sent you a little email about how to, in that last email I sent you how to do that, or to figure out how to do it. So you're going to get 0.799 equals 12 over x. And then again, you just solve for, x, right? And x comes out to be here 15.018. Now notice when you do it this way, it's a little bit off, right? Because it's really going to be 15. But again, remember, when you're doing trig functions that don't come out to be nice, simple numbers like a half or 1 or something like that, sometimes we can get them, those special ones, 30, 60, and 45 in radical form, like radical 3 over 2, radical 2 over 2. But for these other ones, they're going to be irrational numbers. So they're really going to be long decimal numbers. And of course, if we don't, the more you round off, it just means your answer is going to be a little rounded off. So although the exact answer is really 15, it just comes out to be 100th off or so. And that's because of the rounding error. Okay. Now, another thing to keep in mind when you're doing trig problems, which really is a geometry idea, is any time you know 2 or 3 angles in a triangle, it doesn't have to be a right triangle, you automatically can figure out the third angle because there's 180 degrees in every triangle. So if we wanted to find this angle up here, you don't even need the trig. You could just say it's going to be 180 minus 90 minus the 53.13, and you get this, okay? All righty. Okay. Now here's another example of a kind of problem you want to look at. So let's say you have a problem like this. Suppose you're told Here's a triangle. Here's an angle. Now, we know right away that the sine of the angle, since this is a right triangle, is 2/3, right? But suppose you want to find all 6 trig functions, right? So right for starters, you know that the sine of the angle is 2/3, right? 2/3. Now, a good way to do a problem like this is start off by using the Pythagorean theorem to find this side, right? So that's going to give you 2 squared, call this side x, plus x squared equals 3 squared. Solve, you're going to get 4 equals x squared. 4 plus x squared equals 9. X squared equals 5. So this side here is going to be the square root of 5, right? That's the square root of 5. So once you know that, now you can do everything, because right away, even before you did this, if the sine is 2/3, the cosecant, which is the reciprocal of the sine, remember, technically, you can think of it as 1/2, but again, the simpler way, what that'll come out to equal is just when it's a fraction, just flip it to get the reciprocal. So the cosecant will equal 3/2. Now, we know, again, by Pythagorean theorem, this is radical 5, so the cosine is going to be radical 5/3. The secant, its reciprocal, is going to be 3/radical 5. And again, usually, remember in algebra, we rationalize the denominator, so multiply top and bottom here by radical 5. So you get 3/radical 5/5, right? Radical 5 times radical 5 equals 5. And the last one, we're going to get that the tangent of theta is opposite over adjacent. Remember, we figured this is radical 5. So it's 2/radical 5. Rationalize the denominator. So we get top and bottom times radical 5. We get 2/radical 5/5. Now, to get the cotangent, you get the reciprocal. Now, a little tip here. You could take the reciprocal of this rationalized version, or you could take the reciprocal of the original one, right? Now, see here, it's actually easier to take the reciprocal of this one, because right away, you get radical 5/2, and you're done. If you did it this way, you take the reciprocal of this, you get 5/2 radical 5. And then when you simplify that by rationalizing the denominator, you're still going to get this anyway. But it's just quicker if you just take this one and get the reciprocal, okay? And then there's another little problem down here. I think this is similar to one we already did in class, so I'm not going to go over that right now with you. You can just look at that. Okay. Then the next thing I want to go over in the notes was this one. Now, the purpose of this is to show you that right triangle trig can often be used in something that is called triangulation. In other words, what that means is sometimes there's real situations where you want to find certain distances, and it's not very practical to just take out a ruler or a tape measure and measure how long they are, right? Why? Well, maybe the distance you're trying to measure is really large. Like maybe you're trying to measure the distance from here, this is what astronomers use this a lot, to some star somewhere else in our galaxy, right? Well, obviously, you're not going to take out a ruler and measure the distance to a star in our galaxy. Or you're not even going to take out a ruler and measure the distance to something that is maybe a half a mile away, right? So that's one reason why sometimes you can't measure things. Sometimes the reason you can't measure straight distances is it might be over water, right? Where you'd have to measure over, let's say, 50 feet of water, right? Now, again, you could sometimes do that if you had a boat and you could kind of, speedboat or a rowboat, and you could like pull the boat along and if you had a long ruler, you could do it that way. But usually, again, that sometimes is very impractical. Another thing that's sometimes is very impractical to measure is the things that are really tall, like the height of a tree or the height of a building, just real easily with a ruler, right? So this is where this idea in trigonometry that we're studying now, right triangle trig, comes into play. Because a lot of times what you can do is you can imagine, usually the triangle is not there, a physical triangle, but you can imagine a triangle, including the part that you want to measure how long it is. And then very often there's another part of the triangle that you can actually see how long it is, or know, or figure out how long it is. And there's an angle sometimes that you can measure. And then by imagining the triangle, you can actually figure out certain distances that you couldn't normally measure, right? So let me give you an example of this. So here's an example. So let's say someone says there's a balloon, let's say a hot air balloon, and let's say it's way up high in the air, and let's say it's tethered to the ground with a little rope here, right? A thin little rope, but it's secure, and it's way high up in the air. This hot air balloon. Maybe it's just staying there with a big sign on it to advertise something, or whatever it might be. Now, suppose you want to figure out how high up is the balloon, right? How high up is the balloon? Well, normally it'd be very impractical to measure that, right? With a ruler, right? You'd have to have a really long ruler, right? You just couldn't do that. And it's just hard to have a ruler go straight up like that. So what you can do is this. You could, let's say, go the length of a football field in this direction, right? And you can measure 300 feet. That's not too hard on a flat surface. There's tape measures, special tape measures that, or 100-foot tape measures. You could just do that times 3, do 3 of those or whatever. It doesn't have to be 300 feet. It could be 100 feet. But let's say you walk what you know is a distance of 300 feet in this direction, okay? Now, then what you do is you look up at so you're angling from the ground right to the hot air balloon. This angle right here. This is your sight angle, right? Now, again, you might not right away know what this angle is, but when people do this kind of thing, a lot of times you see surveyors out surveying properties. They're looking through a special tripod, and they have a special piece of equipment. What they're doing usually is, you guys know, like a protractor measures angles, right? So what they have is an instrument which is called a sextant. Now, what a sextant is, it's a special instrument that is really a glorified high-tech protractor for measuring angles, but it has a sight through it. So you can very accurately sight in this direction, then you turn the little telescope sighting thing you're looking through, and you sight right to the balloon, and it measures the angle that you had to turn on the piece of equipment to sight from here to here. And you can pretty accurately see what that angle is. That's what surveyors are doing all the time. Usually they're not necessarily measuring angles up in the air. They're measuring maybe left, right, but it's the same idea. So you could figure out, measure that this angle is 38 degrees, right? Now, very often in these kind of problems, built into the problem is a right angle. Because if the ground, let's say, is flat and the balloon is straight up and there's no wind, we're going to assume this is a right angle. Sometimes you might have a situation where this is a building. We're going to assume the buildings, go straight up, right angle to the ground, right? And also notice we just have this distance and this distance. But now the key here is you can imagine a triangle here, right? You see, this dotted line is an imaginary line. It's not really there, but we can imagine the triangle. Now, we can do this just like the problems we were doing for homework. If this is a right triangle, this is 38 degrees. This side is 300. This side we want to figure out, call that X or question mark. We now know we want to use the tangent. Remember, you always know you want to use the trig function of the angle that uses the two sides of the triangle, that it might be the hypotenuse sometimes. The two sides should be the one you know and the one you got to figure out. So here, this is the adjacent, this is the opposite. That's the trig function that uses the tangent, right? So the tangent of 38 is going to be h over 300. Then, again, you just say that h is going to equal 300 times, just bring the 300 to this side, times the tangent of 38. And now, and again, sometimes, folks, to get more accuracy, you can do this in one step. Now, you can figure out the tangent of 38 and then multiply it times 300, or you can just put into your calculator 300 times tangent of 38. And to the nearest foot, we would get, let's say the problem says to the nearest foot, that this balloon would be 234 feet up in the air. You see? But you see how you can figure that out without actually measuring its height. You're doing everything on the ground. You're just going 300 feet, measuring in this direction. And then with, like I said, that special piece of equipment where you can measure like a protractor very accurately through a little thing that sights things, like on the sight on a, that you see this sometimes on a camera, sometimes on rifles, where you can, sort of, look at a certain particular point in the distance. So you can angle this way and this way, and it's designed to have, it has a protractor built into it to see what that angle is there. Okay. Now, one other thing I want to mention, very often when you do these kind of problems where you're coming from the ground and something's up in the air, the angle that you sight up at from the ground, sometimes that's called the angle of elevation. So in this problem, the angle of elevation would be 38 degrees, you see? Also, sometimes if you're actually measuring down, right? Let's say someone was up here. What they could do is imagine they're up here, let's say in the balloon. You can imagine a horizontal line going parallel to the ground, right? So sometimes they could actually do the measurement from up here. They could imagine a horizontal line going up here parallel to the ground. When they sight down from this imaginary parallel line to where you are down here, this angle, because you're going down, we call the angle of depression, right? It's just called the angle of depression. It's not like an angle that's sad or anything. It means like depression as in going down. So, and if you remember from parallel lines in geometry, since this line is parallel to this line, and this is the sight line, which is sort of the transversal, the angle of depression will always equal the angle of elevation. It's just two different ways of measuring it, okay? But they're actually the same thing in size. Okay, but again, when you get these problems for homework, what you always want to do is first draw the picture with the imaginary triangle that sort of represents what the picture is talking about, right? Then you fill in what you know, and then you set up the right trig equation to solve it, right? Okay. Now, the very last thing I wanted to go over with you is we're not going to be really doing hardly anything in section 4.6. We're not going to really have the time this semester because, like I said, we're losing a full week of class because we had 2 weeks for vacation. And, to do this section really well, we take at least another class or so. But I just want you to be aware of this. This is a section what's called trig identities. Now, all trig identities means, it means things that are trigonometric function relationships that are always true no matter what angle you have. So, for example, we already have the one that basically says, it's really the Pythagorean theorem in disguise, sine squared theta plus cosine squared theta equals 1, right? And remember, when we write this, like I just said earlier, this really means sine of theta times sine of theta. This means cosine of theta times cosine of theta. Now, I just want you to look at a couple of these other ones that are just sort of nice to know. But again, you're not going to really have to know these for the test. I just want you to be aware that they're out there. See, this one says, if you take the sine of the opposite of an angle, let's say it's positive, this one would be negative, that'll equal the opposite of the sine of the angle. For example, we know that the sine of 30 degrees is a half. So if you make it negative, it's minus a half. But that would equal the sine of minus 30 degrees, because you're going down, would be negative a half, right? So, these are just some things you just want to be, you can just look at how they work. Sometimes the way these things can, where you can figure out these things from is by doing algebra. This one says that sine plus cosine of an angle, and you square that, that'll equal this. 1 plus twice sine theta plus cosine theta. The way you can notice this one is if you multiply this out like a FOIL, sine of theta plus cosine theta times sine of theta plus cosine theta, you're going to get a sine squared term, you'll get a cosine squared term, but those two, sine squared plus cosine squared equals 1, and for the inner and outer, you're going to get sine of theta, cosine theta, so there's this. So sometimes the way you can see that these identities work is through algebra manipulation, in addition to some trig ideas. But basically, I just wanted you to see this idea what trig identities are, but we're not going to have a lot of time to spend much on it. I just want you to be aware of that. The most important one you want to remember is this one, right? This is the key one we'll be using. Okay, so I guess that's going to be it. If you have any questions about this, you can send me an email, or you can just wait till Monday. Also tomorrow, which will be Friday or Saturday, by Saturday, I'll send you just some review ideas and some problems you should look at. There would be good sample problems, representative problems that will be similar to the ones on the test, right? Okay, guys, that's about it for now. So I'm going to be signing off.